Hi everyone! In today's video, my friends and I will present a material about bilinear transformation. My name is Alia Maharani and my friends are Dias Kurotun Ayuna and Faisal Fazri Akmal. We are from Group 6 of Complex Analysis lesson. We've got three main topics here. The first is linear fractional transformation that will be presented by me. The second is an implicit form that will be presented by Dias. And the last is mappings of the upper half plane that will be presented by Faisal. Okay, let's get started. Linear fractional transformation. The transformation W equals to AZ plus B over CZ plus D, where A, B, C, and D are complex constants, is called a linear fractional transformation or Mobius transformation. Equation 1 can be written in the form AZW plus BZ plus CW plus D equals to 0. And conversely, any equation of type 2 can be put in the form 1. Since this alternative form is linear in Z and linear in W, another name for a linear fractional transformation is bilinear transformation. When C equals 0, the condition AD minus BC equals to 0 with equation 1 becomes AD equals to 0. And we see that the transformation reduces to a non-constant linear function. When C is not equal to 0, equation 1 can be written W is equal to A over C plus BC minus AD over C times 1 over CZ plus D. Equation 3 reveals that when C is not equal to 0, a linear fractional transformation is a composition of the mappings. Z equals to CZ plus D, W is equal to 1 over Z, W is equal to A over C plus BC minus AD over C times W. Regardless of whether C is 0 or non-zero, any linear fractional transformation transforms circle and lines into circles and lines, because this special linear fractional transformation do. Solving equation 1 for Z, we find that Z is equal to minus dW plus B over CW minus A. When a given point W is the image of some point Z under transformation 1, the point Z is retrieved by means of equation 4. If C equals to 0, so that A and B are both non-zero, each point in the W plane is evidently the image of one and only one point in the Z plane. The same is true if C is not equal to 0, except when W is equal to A over C, since the denominator in equation 4 vanishes if has that value. We can, however, enlarge the domain of definition of transformation 1 in order to define a linear fractional transformation T on the extended Z plane, such that the point W equals to A over C is the image of Z equal to infinity when C is not equal to 0. We first write Tz is equal to Az plus B over Cz plus D. Then T infinity is equal to infinity if C equals to 0. And T infinity equals to A over C, and T minus D over C is equal to infinity if C is not equal to 0. When its domain of definition is enlarged in this way, the linear fractional transformation 5 is a 1-to-1 mapping of the extended Z plane onto the extended W plane. That is, tz1 is not equal to tz2 whenever z1 is not equal to z2. And for each point in the second plane, there is a point z in the first one, such that tz is equal to w. Hence, associated with the transformation t, there is an inverse transformation t power minus 1, which is defined on the extended w plane as follows. Inverse transformation w is equal to z if only if tz is equal to w. From equation 4, t power minus 1 w is equals to minus dw plus b over cw minus a. Evidently, the inverse transformation itself a linear fractional transformation, where inverse transformation of infinity is equal to infinity if c equals to 0, and inverse transformation of a over c is equal to infinity, and inverse transformation of infinity is equal to minus d over c if c is not equal to 0. If t and s are two linear fractional transformations, then so is the composition stz. This can be verified by combining expression of the type 5. Note that, in particular, the inverse transformation of tz for each point z in the extended plane. There is always a linear fractional transformation that maps three given distinct points z1, z2, and z3 onto three specified distinct points w1, w2, and w3 respectively. Verification of this will appear in the next section, in the section An Implicit Form, where the image w of a point z under such a transformation is given implicitly in terms of z. We illustrate here a more direct approach to finding the desired transformation. Example 1. Let us find the special case of transformation 1 that maps the points z1 equals to minus 1, z2 equals to 0, and z3 equals to 1. Onto the points, w1 is equal to minus I, w2 is equal to 1, and w3 is equal to I. Since 1 is the image of 0, expression 1 tells us that 1 is equal to p over d, or d equals to p. Thus, w is equals to az plus p over cx plus p. p a minus c is not equal to 0. Then, since minus 1 and 1 are transformed into minus I and I respectively, it follows that IC minus IB is equals to minus A plus B, and IC plus IB is equals to A plus B. Adding corresponding sides of these equations, we find that C is equals to minus IB, and subtraction reveals that A equals to IB. Consequently, W is equals to IBZ plus B over minus IBZ plus B equals to B IZ plus 1 over B minus IZ plus 1 is equal to IZ plus 1 over minus IZ plus 1. This is the same as W is equals to I minus Z over I plus Z, which is obtained by assigning the value I to the arbitrary number B. Example 2. Suppose that the points z1 equals to 1, z2 equals to 0, and z3 equals to minus 1 are to be mapped onto w1 equals to I, w2 equal to infinity, and w3 is equal to 1. Since w2 is equals to infinity corresponds to z2 equals to 0, from equation 6 and 7, that c is not equal to 0 and d is equals to 0 in equation 1. Hence, w is equals to az plus b over cz, where bc is not equal to 0. Because 1 is to be mapped onto I and minus 1 onto 1, we have the relations IC is equals to a plus b, and minus c is equals to minus a plus b. And it follows that 2a is equals to 1 plus I times c, and 2b is equals I minus 1 times c. If we multiply numerator and denominator in the quotient 13 by 2, make these substitutions for 2a and 2b, and then cancel out the non-zero number c, we arrive at w is equals to I plus 1 times z plus I minus 1 over 2z.
The next material is about an implicit form. The definition is the equation w minus w1 times w2 minus w3 over w minus w3 times w2 minus w1 equal to z minus z1 times z2 minus z3 over z minus z3 times z2 minus z1. We called it with equation 1. Defines implicitly a linear fractional transformation that maps distinct points z1 and z3 in the finite z plane onto distinct points w1, w2, and w3 respectively in the finite w plane. Means that the two sides of equation 1 are cross relations, which play an important role in more extensive developments of linear fractional transformations. And the next, to verify this, we write equation as z minus z3 times w minus w1 z2 minus z1 times w2 minus w3 equal to z minus z1 times w minus w3 times z2 minus z3 times w2 minus w1. We called it by equation 2. And if z equal to z1, suppose that if z equal to z1, the right hand side of equation is 0. And it follows that w equal to w1. Similarly, if z equal to z3, the left hand side is 0 and consequently w equal to w3. If z equal to z2, we have the linear equation w minus w1 times w2 minus w3 equal to w minus w3 times w2 minus w1, whose unique solution is w equal to w2. One can see that the mapping defined by equation 1 is actually a linear fractional transformation by expanding the products in equation 2 and writing the result in the form azw plus bz plus cw plus d equal to 0. We called it with equation 3. The condition AD minus BC not equal to 0, which is needed with equation W3 is clearly satisfied since, as just demonstrated, equation 1 does not define a constant function. For the clear explanation, we go to the example 1. The transformation required that Z1 equal to -1, Z2 equal to 0, Z3 equal to 1, and W1 equal to -I, W2 equal to 1, and W3 equal to I. Using the equation 1 to write W minus I times 1 minus I over W minus I times 1 plus I equal to Z plus 1 times 0 minus I over Z minus 1 times 0 plus 1, and then solving for W in terms of Z, we arrive at the transformation W equal to I minus Z over I plus Z found earlier. If equation 1 is modified properly, it can also be used when the point at infinity is one of the prescribed points in either the extended Z or W plane. Suppose, for instance, that Z1 equal to infinity. Since any linear fractional transformation is continuous on the extended plane, we need to only replace Z1 on the right hand side of equation 1 by 1 over Z1 clear fractions and let Z1 tends to 0. So we determine the limit value. Lim Z1 tend to 0 for Z minus 1 over Z1 times Z2 minus Z3 over Z minus Z3 times Z2 minus 1 over Z1, we times this fraction with Z1 over Z1, and then we get lim Z1 tend to 0 for Z1Z minus 1 Z times Z2 minus Z3 over Z minus Z3 times Z1 Z2 minus 1. We get the result Z2 minus Z3 over Z minus Z3. The desired modification of equation 1 is W minus W1 times W2 minus W3 over W minus W3 times W2 minus W1 equal to Z2 minus Z3 over Z minus Z3. Note that this modification is obtained formally by simply deleting the factor involving Z1 in equation 1. It is easy to check that the same formal approach applies when any of the other prescribed points is infinity. The second example, the prescribed points are Z1 equal to 1, Z2 equal to 0, Z3 equal to minus 1, and W1 equal to 1, W2 equal to infinity, and W3 equal to 1. In this case, we use the modification of equation 1. W minus W1 over W minus W3 equal to Z minus Z1 times Z2 minus Z3 over Z minus Z3 times Z2 minus Z1, which tells us that W minus I over W minus 1 equal to Z minus 1 times 0 plus 1 over Z plus 1 times 0 minus 1. We only substitute the value of Z1, Z2, Z3, W1, W2, and W3. Solving here for W, we have the transformation obtained earlier. W equal to I plus 1, Z plus I minus 1 over 2Z.
The next material is about the mappings of the upper half plane. Let us determine all bilinear transformation that map the upper half plane of the positive imaginary Z onto the open disk, the absolute of W less than 1. and the boundary of imaginary z equal to 0 of the half plane onto the boundary of absolute of w equal to 1 after this. First, select the point z equal to 0, z equal to 1, and z equal to infinity on the line imaginary z equal to 0. Then, determine condition on bilinear transformation which is necessary for the image to have unit modulus. Then we have the W is equal to AZ plus B over CZ plus D with the requirement that AD minus BZ is not equal to 0. If the absolute of W equal to 1 when Z equal to 0, then we have the absolute of B over D equal to 1. That is, the absolute of B equal to the absolute of D and it is not equal to 0. The image of z equal to infinity is a finite number only if c is not equal to 0. If the absolute of w equal to 1 when z equal to infinity, then we have the absolute of a over c equal to 1, or the absolute of a equal to the absolute of c, and this is not equal to 0. Based on the requirement 1, 2, and 3, we can write the form w equal to a over c times z plus b over a over z plus d over c. Then, since the absolute of a over c equal to 1 and the absolute of b over a equal to the absolute of d over c and this is not equal to 0, we can write the w equal to exponential I alpha times z minus z0 over z minus z1 with the requirement the absolute of z0 equal to the absolute of z1 and this is not equal to 0. Impose that the absolute of w equal to 1 when z equal to 1, we get the absolute of 1 minus z1 equal to the absolute of 1 minus z0. And we have 1 minus z1 square equal to 1 minus 0 square. But we have that z1 times the conjugate of z1 equal to z0 times the conjugate of z0, since the absolute of z1 equal to the absolute of z0. Then we have z1 plus the conjugate of z1 equal to z0 plus the conjugate of z0, which means the real z1 equal to the real z0. Based on the requirement 6, it follows that either z1 equal to z0 or z1 equal to the conjugate of z0. If z1 equal to z0, the transformation 5 becomes w equal to exponential I alpha. Hence, we get that the z1 should be equal to the conjugate of z0. The transformation 5 with z1 equal to the conjugate of z0 maps the point z0 onto the origin w equal to 0, and since points interior to the circle the absolute of w equal to 1 are to be the images of points above the real axis in the z-plane, we may conclude that imaginary of z0 is positive. Thus, all bilinear transformations that have properties A and B can be the form W equal to exponential of I alpha times z minus z0 over z minus conjugate of z0 that have requirement that imaginary z0 is positive. It remains to show that, conversely, any linear fractional transformation on the form 6 has the desired mapping property. This is easily done by taking the modulus of each side of equation 6 and interpreting the resulting equation. That we have the absolute of W equal to the absolute of Z minus Z0 over the absolute of Z minus conjugate of Z0 geometrically. If a point Z lies above the real axis, both it and the point Z0 lie on the same side of the axis, which is the perpendicular bisector of the line segment joining Z0 and the conjugate of Z0. It follows that the distance, the absolute of Z minus Z0, is less than the distance, the absolute of Z minus conjugate of Z0. That is, the absolute of W less than 1. Likewise, if Z lies below the real axis, the distance of the absolute of Z minus Z0 is greater than the distance, the absolute of Z minus conjugate of Z0. And so we have the absolute of W is more than 1. Finally, if Z is on the real axis, we have that the absolute of W equal to 1, because then the absolute of Z minus Z0 equal to the absolute of Z minus conjugate of Z0. Since any linear fractional transformation is one-to-one mapping of the extended Z plane onto the extended W plane, this shows that transformation 6 maps the half plane of positive imaginary Z onto the disk, the absolute of W less than 1, and the boundary of the half plane onto the boundary of the disk. For the example, we have the transformation, the W equal to I minus Z over I plus Z. It can be written as W equal to the exponential of I P times Z minus I over Z minus conjugate of I. Hence, the transformation have the property to map the upper half plane of positive imaginary Z onto the open disk, the absolute of W less than 1, and the boundary of imaginary Z equal to 0 of the half plane onto the boundary of the absolute of W equal to 1 of the disk.
Thank you for watching. We hope that our presentation is useful for you. See you on our next video. Bye!